everybody. I'm Grace, and finally I get to give my presentation. I study mechanical and ocean engineering at MIT with a focus on underwater robotics. And these pictures show some of the systems I worked on in the past for seafloor mapping, seabed oil detection, and autonomous navigation. And now this summer, thanks to the Hollings Scholarship Program, I got the chance to apply my interest in marine robotics in Hawaii for NOAA's Pacific Islands Fisheries Science Center. And there, I built a robotic camera system for monitoring fish. Before I go into technical details on the system, I'm going to explain why NOAA is interested in monitoring fish. And when I say monitor, I mean measure the abundance and size of fish based on video footage from fish and their habitat. And this data not only improves our understanding of the ecosystems, but also helps NOAA management make informed decisions about how to keep oceans healthy and fisheries sustainable. As background, there's 3 types of fishing that happen in Hawaii. There's shallow or reef fishing, pelagic or open ocean fishing, and bottom fishing. And the system I worked on was built on monitoring the bottom fishing, which happens about 100 to 400 meters deep. And NOAA, because it's part of the Department of Commerce, is focused on monitoring the 7 most commercially important bottom fish, which are referred to as the deep 7 species in Hawaii. And those are pictured here. There's opakapaka, onaga, and others you can see at the grocery store in Hawaii. To ensure against overfishing in Hawaii, the state and NOAA enforce 2 restrictions. The first is that there's an annual catch limit. So commercial fishermen must report all their catch, and once the total allowable catch, or TAC for the year is reached in terms of pounds per fish, the fishing season is closed for the year. And then they have bottom fish restricted fishing areas, or BRFAs, which are special kind of marine protected areas where it's illegal to fish for bottom fish. And to give you a sense, there's 12 of those areas. They're shown here on the map in red. The idea is that in these red zones, fish can grow without the pressures of fishing. And over time, researchers will be able to study these areas versus the fished areas to help determine some of the effects of fishing. And now, believe it or not, this brings us back to robots. So this system is called BotCam, and it was developed by another engineer for the Pacific Islands Fisheries Science Center, an engineer named Darren Merritt. And he designed the system to monitor the commercially important bottom fish off the Hawaiian coasts. And the work I did this summer was built off the previous work by Danny. It has 2 cameras, so it has stereo vision, and it can gauge depth this way. It also was the first system of its kind to be able to use stereo vision at up to 300 meters deep using only ambient light. Researchers didn't want to use an external light source because it would either attract or scare away fish and bias the measurements. And it's got an arm-carrying bait in between the cameras, and this attracts fish from a small radius around the robot to the front of the camera so that they can be measured. And hopefully the concept behind BotCam sounds simple, but it's not really. The cameras and the electronics on the system were quite complicated. So it weighed about 300 pounds and had to be deployed from a rather sizable vessel, like in the picture here with an A-frame and hydraulics. Also, at this point, the cameras on the system are outdated. They could often return low-quality footage that made it hard to accurately identify fish species and length. Also, the cameras were analog, so they required an external synchronization and could often fall out of sync, which affects the precision of measurements. And that brings me to my project this summer, which was to design a whole new system to replace BotCam. And that system is called MOUSE, the Modular Optical Underwater Survey System. And it has the same abilities as BotCam, but it's about 1/3 of the weight. So it can be deployed from much smaller research vessels at much less cost. It's also got better cameras with a higher frame rate and higher resolution so that fish identification and length measurements can be more accurate. Also, and it's got a fast Ethernet connection that will allow data download to be twice as fast as on the old system. And the cameras are digital, so they don't need an external synchronization and they won't fall in and out of sync. It's autonomous, meaning once it goes in the ocean, it doesn't need humans telling it what to do. And it's modular. It can be deployed on its own as a stationary system, like in this picture, or it can be attached to another vehicle. In terms of methods, I created this 3D model of the system on the right using modeling software on my desktop. And then I was talking a lot with people. I talked to researchers who use BotCam and the crew who deployed BotCam from a boat to see how they wanted it improved and how I could make their lives easier. I also spent some days just driving around the island to machine shops and hardware stores while this was getting fabricated. The core of the system is the base bar, which contains all the electronics. And it's modular, meaning it can act on its own or it can attach to another system, such as an AUV, an autonomous underwater vehicle, or an ROV, a remotely operated underwater vehicle. Right now, a version of the mouse cameras are attached to the AUV in this picture. And this is from just last Friday, by the way, my last day on the job. It could also attach to the ROV here in the red box, although it's not attached yet. And now, briefly, I'll go through each of the electronic components on the base bar. Probably most importantly, there's the cameras. These are not normal cameras. They are Prosilica GT1920 cameras with modified software by Seabed Technologies. And we chose these because they're ultralight sensitive. They will be able to collect usable footage at 250 meters deep in the ocean, or even 300 meters deep on a very clear day. And this is what the world will look like to mouse through those cameras. It sees black and white high-resolution images, and at those depths, colors are pretty saturated, so the color information would be unnecessary. Also, keep in mind the 7 fish we're looking at identifying are mostly distinguished by their size and by the stripes on them, not by the color. So again, we don't need the color information. Then also, another thing to note is that it sees double. The 2 images are what allow the system to gauge depth and the length of fish in space. The cameras are powered by this 16-pound lithium-ion battery that can power the system for up to 8 hours. And the images from the camera are stored on the DVR, or digital video recorder. This is made up of 2 500-gigabyte solid-state drives, so it can store images from a full day's worth of data collecting. Just to show you again how it all connects together, this is the base bar and the electronics, which together weigh 40 pounds. And then when it's acting on its own, not connected to an AUV or ROV, it's enclosed in a stainless steel cage that weighs about 20 pounds on its own. And then the cage has a bait arm in the middle, like on the BotCam system, and then lines that connect it to an anchor on the bottom and floats on the top that make the system neutrally buoyant. Now here's some of the blueprints I made for various components on the system. The crew who used BotCam before me gave me some useful feedback that was easy for me to implement on the new system. For example, they said it'd be easier for them if the units could stack on top of each other. So I added pegs in the corners of the cage that would let them stack like IKEA boxes. And I feel lucky because it's rare you get to see a project go from its initial concept to its final fabrication. But that's what I got to do this summer with Mouse. I made this 3D model of the system in my first month. And then this picture is from the pool test we did with the finally built system. And that pool test was last week. And the next step is literally happening as we speak. My wonderful mentor, Dr. Ben Richards, is in the middle of the Pacific Ocean, dropping Mouse and BotCam in the ocean and collecting data with them and comparing their results. Also, the big picture here is that we have another way to monitor the health of the oceans and collect meaningful data that will better inform NOAA management decisions on the placement of the marine protected areas and on the annual catch limit each year. And this can help keep the fishery sustainable in the years to come. And finally, I have a long list of people to thank, especially my mentor, Dr. Ben Richards, and the people in Jeff Drazen's lab at University of Hawaii. Any questions? I'll take them now. Thank you.
This could be equally as well used, not just for the bottom, but
could be, although I think to identify reef fish, you probably want a color system because the fish are prettier and they're more colors, yeah. It's continuously running. It takes 40 frames per second, so high resolution video footage. And it's, you turn it, turn it on an on switch before you drop it in the ocean. Oh, each of the cameras is $8,000. It's expensive. They're shooting Ripley 4, but they have huge dome-shaped lenses on them, so they have like a 160-degree field of view. It's pretty huge. It's like the GoPro field of view. Definitely. In fact, the Northwest Fisheries Center wants to use the same system. That's why we're probably going to make 10 of them that'll be ready in November that they'll be using to monitor fish.
Any comments or questions for the judge? All right. Can you believe it? You're done.